All right, so delta H is the change in enthalpy of reaction. The rest of the chapter is how do we measure and use delta H reaction, what does it mean, because it's going to be an amount of heat energy, we're going to say things that relate it to the number, or to the potential energy of the reactants and products. All right, but we need a system for measuring it, for calculating it, and here's our first one. We use a coffee cup calorimeter. A coffee cup calorimeter is literally 2 coffee cups. Styrofoam is best because they are the most insulating. Put an insulated cover on top, a thermometer, a stir bar. You can also swirl so that you don't need the stir bar. And then we have some solution in here, or some water, as we'll see. All right, so we will see that when we place reactants inside cups, that the system will typically be 75% plus reaction, 25% material. And I'll show you again what this means more specifically. Again, that is the definition of the system. The surroundings is everything else. Including the water or solution. And the assumption when using a coffee cup calorimeter is that the coffee cups are perfectly insulating. Which means no heat escapes or goes into the coffee cups. No heat goes into coffee cups. And therefore, all of the heat from the system, whether it's a reaction or material, all heat from system goes to surroundings. And I'll show you on the next page, we have an equation that does that. Q, lowercase q, is our symbol for heat. So Q for the system equals minus Q surroundings. And the minus sign only shows up because there's a change in the direction of heat flow. If the system is giving off heat, then the surroundings is taking heat in. There's a directional difference there, and that's what the minus sign means. The Q system could be positive or negative, doesn't matter, it depends on if the reaction, if it's a reaction is endothermic or exothermic. All it says is if this gives off energy, this takes it in. If the reaction system takes in energy, then the surroundings are giving off energy. All right, so now we have the coffee cup calorimeter equations. I'm going to ask you to draw a line down the middle. We do have 2 cases. We have that the system is a reaction. And we have the system as a material. So similar, though, I think it's best to keep these 2 sets of equations separate in your mind. I don't know, we'll see as we go. System as a reaction, then Q system becomes Q reaction. It is equal to minus Q of the surroundings. And what we will see is that the surroundings in the coffee cup calorimeter will be everything, but since the coffee cups keep all of the heat energy inside, then functionally the surroundings are the solution inside the coffee cups. Now I'm going to keep working these. So the solution, and remember Q is heat. Q solution is going to be the mass of the solution times the specific heat capacity of the solution times the temperature change of the solution, where temperature change will always be the final temperature of the solution minus the initial temperature. And that goes for all changes. It's always final minus initial. Okay, now a couple things about the solution. So, and we'll see this in our examples. The solution will be an aqueous solution in which water is the solvent, and it will be 90+% water, which means we can make two assumptions. One is that the specific heat capacity of the solution is equal to the specific heat capacity of water. Which is 4.184 joules per gram degree Celsius. The other is that the mass of the solution, the density of the solution is the same as the density of water. And where the density of water is 1.00 gram per milliliter, which means that in a problem, if I say there are 250.0 milliliters of a certain solution, we can assume that that is 250 grams of solution. Okay. All right. So that's the setup. That's the solution part. Now let's do Q reaction. Q reaction is going to be the one that's quite different. It is going to involve our delta H of reaction, since there is a reaction in this problem. And that's going to be times moles reacted. And it won't come up very much, but these are moles reacted with a 1 coefficient. We saw that coefficients matter in their relationship to delta H. If it comes up for us, I'll let you know. All right, so, and the way that you solve problems is there are 1, 2, 3, 4, 5, 6 different things that you need to know. And of course, in typical Chem 1010 fashion, we'll give you the information for 5 of them, and you'll have to solve for the last one. The last one mostly being delta H reaction that you'll have to find. Anyway, we'll do some problems coming up, but this is the overall setup. It's similar when the system is a material. Let's assume that the material is aluminum, and that aluminum is being placed in, will typically be placed in water. So aluminum, so placed in water. The material is typically placed in water. You'll see a couple times where there's 2 different materials, but typically it's a solid placed in a liquid at least. This time it's the heat of the aluminum equals minus Q, or the heat of the water. So this just says all the heat given off or taken in by the aluminum goes to the water, or comes from the water. Now these are 2 materials. These materials, so no reaction involved. They will both have identical terms to this solution part over here, meaning that Q aluminum equals the mass of the aluminum times the specific heat capacity of the aluminum times the temperature change of the aluminum. Same thing for water, mass of water. Times the specific heat capacity of the water times the temperature change of the water. And I think the one thing that comes up pretty frequently in these types of problems is that we're solving for T final, and that in these types of problems, T final is the same for the aluminum and the water because you'll be mixing them together. So T final is the same for aluminum and water. You won't in fact have two separate T finals. They'll both be the same, and that's what you'll be solving for, as I think we'll see. That seems like a good place to stop. We'll save the example